For this lesson, we're going to talk about our trig functions being either even or odd. If you'll recall, we talked about whether sine, cosine, and tangent were even or odd whenever we were going through their graphs. And so this is going to do nothing but just back up what we figured out by looking at their graphs. Remember, a function graphically is odd if it's symmetric about the point of origin. And we remember that both sine and tangent, the graph of both of those functions, we determined graphically were odd, and so analytically we're going to back that up with these even-odd identities. And we also determined that a function is even if it is graphically symmetric about the y-axis, and we determined that the cosine function was indeed even because that's what its graph looks like. So all functions, including trig functions, can be described as being even, odd, or neither. Knowing whether a trig function is even or odd can help us simplify an expression. So these even-odd identities are helpful when we have an expression where the variable inside the trig function is negative, such as negative x. So remember, analytically what we're looking for in an odd function is that if we take a negative input value, negative x, and feed it into an odd function, when we clean it up algebraically, or now we're going to see trigonometrically, that negative sign will pop out front. In other words, it will give us the opposite sign to the original function we started with. For an even function, when we feed that function a negative value, we get the original value, the original function, back with no changes in the output values at all from the original function f of x. So let's take a closer look. Let's go back to our unit circle, and we're going to find the sum of the sine of pi over 3 and the sine of negative pi over 3. So here, in essence, we have the sine of x and we have the sine of negative x. So specifically at pi over 3, we can see that the sine value is positive square roots of 3 over 2. And we can see at negative pi over 3, the sine value is negative square roots of 3 over 2. So it is true that when we put a negative value into the sine function, that negative value pops out front. Therefore, we know sine analytically to be an odd function, and this is what that looks like. The sine of negative theta is going to be equal to negative sine of theta, the opposite of the positive angle measure. Now let's go back to the unit circle and let's see and confirm that cosine is an even function. Same angle measures. We're now looking at the x-coordinates of these points. So the cosine of pi over 3 is positive 1/2, and the cosine of negative pi over 3 is still positive 1/2. And so analytically, that confirms that when we put that negative angle measure value into the cosine function, that we get the original cosine value out that we would have gotten with the positive angle measure. And so analytically, that confirms that cosine is an even function. Now let's lastly take a look at tangent. Same angle measures. We'll look at the tangent of pi over 3 and the tangent of negative pi over 3. And we can guess because sine is involved in this process, and sine changes, S-I-N-E sine, changes its sign, S-I-G-N. Since tangent involves sine, tangent also, as you can see, is going to wind up being an odd function. If we take the y value divided by the x value, we can see that tangent at pi over 3 is going to be positive square roots of 3, and we can see that tangent at negative pi over 3 is going to be negative square roots of 3. So it is true that both sine and tangent are odd functions. When we feed these functions a negative value, that negative pops out front of the entire original function that we started with. So we're going to use this as identities for some of our trig expressions and equations. This follows that the cofunctions for all of the original trig functions, sine, cosine, and tangent, they have those same identities. Since sine is an odd function, cosecant is an odd function. Since tangent is an odd function, cotangent is an odd function. Since cosine is an even function, secant is an even function. So make sure you have these identities written in your notes, because these are the identities we're going to use when we work these even-odd identities. So here it says, for the sine of theta equals 1/2, determine the sine of negative theta and the cosecant of negative theta. So if the sine of theta is 1/2 and sine is an odd function, then when I feed it a negative value, that negative pops out front. So it's very easily, I don't even really need to write on the screen because the sine of negative theta has to be negative 1/2. That negative pops out front. Since the sine of theta, we'll do it backwards. Since the cosecant of theta is 1 over the sine of theta, that would be 1 over 1/2. So the cosecant of positive theta in this instance would be 2, and the cosecant of negative theta would therefore have to be negative 2. So very straightforward, very simple, nothing complicated. If the cosine of positive x is positive square roots of 2 over 2, then find the cosine of negative x. Well, very simply, it's still going to be positive square roots of 2 over 2 because cosine is an even function. So whatever output I get for the cosine of positive x is going to be the same output I get for the cosine of negative x. And that's it. Very simple, very straightforward, very short lesson. Just make sure you have those identities written down. Come to class next time and we'll work some homework problems.